Okay, Unit 6 is on chemical bonding. So we're going to describe the types of bonds that exist and the characteristics of them. So, first, definition. Chemical bonds occur so that atoms have a lower energy state. Now, this is a theme that I've kind of said over and over again, right? The reason why bonds actually occur is because atoms will be more stable when they are bonded than when they are alone, right? The types of bonds we're going to be describing first are what we refer to as intramolecular. The term intra means within. So it's the bonds between the atoms. In the second half of this unit, we'll talk about intermolecular forces, and that will describe how molecules behave. So, first term, electronegativity. Electronegativity is the relative attraction an atom has for electrons in the bond. Okay, so specifically for purposes of bonding, we use the term electronegativity. I know we've used other terms to describe attractions for electrons in the previous unit, but those were more so related to an atom in isolation. Whereas here we're talking about the relationship between electrons and atoms as they are in a bond. Okay. Now from the graphic you can see the electronegativity increases up, right? So electronegativity increases as you go up, and it increases as you go to the right. And this falls in line with what we know about things like effective nuclear charge and radius. So the electronegativity value is always found on your periodic table. There's no need to memorize any of this. Okay, so let's first describe ionic bonding. Ionic bonding occurs when you have two atoms with a large difference in attraction, so a large electronegativity difference, generally about 1.7 difference or greater. This value here is flexible. There will be instances where the number might be greater than 1.7, but it's not ionic, and there are instances where the value will be less than 1.7, but it is ionic. So there's a spectrum, and there's other factors to consider. Just as kind of general cutoff, around 1.7 is what we use, okay? But just know that, there's caveats to everything, really. So an ionic bond occurs. Let's go through the process here. So let's take your typical compound, the most common compound people are aware of, sodium chloride, right? So if I look up the electronegativity of sodium, it's going to be 0.8, and the electronegativity of chlorine is I should look this up. Hold on. Chlorine, it's 3.0. So we're going to take the difference in electronegativity, right? So 3 minus 0.8, difference is 2.2. This clearly identifies as ionic. So what happens if the electronegativity difference is large? Well, you get a complete transfer of electrons. The electron is transferred from one to the other, and in this case, the electron is going to be pulled off of sodium onto chlorine. And the result is that you will have a cation next to an anion, and the attraction, the actual ionic bond, occurs between the ions, right here. That's the ionic bond, the attraction between ions. But you need to understand that in order for that transfer of electron to occur, you have to have a pretty stark difference in electronegativity. Okay? So we have a transfer of electrons. We have these two ions next to each other that are attracting. Ionic bonds are essentially an electrostatic attraction, and thus they are governed by Coulomb's law. And so what Coulomb's law states is that the energy of interaction is equal to the charge of the first particle multiplied by the charge of the second particle multiplied by a constant, but divided by the radii squared. Now, you might see this as distance squared in other variants of this formula. The point being, though, is that the distance plays a role here, and that the larger the distance is, the weaker the energy of attraction. Okay, and vice versa is true. So, like, the shorter the distance, the stronger the interaction. Also, note that Q1 and Q2 being charges are affected by magnitude of charge. Which means you got +1 charges, but you also have +2, you have +3, right? You have -1, you have -2, you have -3. So the magnitude of the charge plays a very big role here. The energy of interaction is going to be significantly greater if your charge values are 2s or 3s as opposed to 1s. Okay, and so we'll talk a little bit more about that in detail later on. So, you're going to observe after calculation a negative sign. It's because one of your ions has a negative. So when you multiply the magnitude of charges with one of them being negative, you're going to end up with a negative value. Okay. So once we form an ionic solid, we form an arrangement called a lattice. And this is a term you're going to see over and over again throughout this unit. Right? A lattice is an organized arrangement in a solid, specifically what we call a crystalline solid. The reason why I specify crystalline is because there's another type of solid called amorphous, and amorphous solids are unorganized. Amorphous solids slowly change their shape over time on their own. Think like silly putty. Silly putty is an amorphous solid, but a crystalline solid is your classic, sodium chloride crystal like this, right here. Okay, so in a crystalline solid for an ionic compound such as this, there's a term that we can refer to. It's called lattice energy. It is the energy change that occurs when gaseous ions form a solid. Now that sounds like a highly specific set of circumstances, right? But essentially, what it tells us is that the higher the value for lattice energy, it's a measure of how strong the ions are attracted to each other. Right? So higher lattice energy, stronger attraction. And vice versa. When ions come together to form a solid, there's a release of energy because you're forming bonds, and we know that forming bonds is exothermic. So the more exothermic the less lattice energy is, because it will be a negative value. It's going to be a negative value. The more stable the arrangement, i.e. the stronger the bond that forms. Okay, so just to kind of do a simple chart, let's say we have a positive and a negative ion that attract each other. Delta E. So in this first instance, the delta E value, whatever amount of value that changes, that goes from here to here, right? Let's call that value X. Okay, but let's consider then another scenario, say where you have charge magnitudes that are larger. Your change in energy will be larger in magnitude. Does that make sense? You're gonna have a greater change in energy if they attract each other more strongly. right? The values, they're both negative, so we're talking about the magnitude here. Okay. So let's make some predictions based on what we know about ionic compounds based on things like their charge and their size. So NaF and Ki. So the first thing you need to do is go through and assess the charges first and then think about the radius. So sodium's a +1, fluorine's a -1, potassium's +1, iodine's -1. Okay, so in both of these compounds, we have positive and -1 charge magnitudes. So that's consistent across the board. So what is not consistent is the radius. What do you know about sodium versus potassium? Yeah, so sodium is smaller than potassium. What do we know about iodine and fluorine? Okay. So does that picture make sense? Based on Coulomb's law, then, if the charge magnitudes are constant, the difference is the size, the radius. The radius is much larger in potassium and iodine, so that means their energy of interaction is going to be less. So you're going to have a greater lattice energy in sodium fluoride due to the smaller size. In the second scenario, we're comparing sodium fluoride with calcium oxide. Now, with calcium oxide, you've got charge magnitudes of +2 and -2. So sodium, even though calcium is larger than sodium, the magnitude is more influential than the distance. So if you see a larger charge magnitude, it kind of doesn't matter what the radius size is. So immediately we know that calcium oxide is going to have a greater lattice energy. Not only that, you have +2 and -2, right? So you could have like a compound with like +2 and -1, right? You can have like +1, -2, but here both of these are +2, -2, so that's definitely stronger. Aluminum chloride versus calcium chloride. I'll say chloride is constant between these two, but the difference here then would be that your charge on aluminum is +3 and your charge on calcium is +2. So therefore, which one is stronger? Yeah, aluminum. And that means when aluminum chloride forms versus when calcium chloride forms, the formation of aluminum chloride will result in more energy released because the bond that's forming between aluminum chloride is stronger than the bond between the calcium and chlorine. Does that make sense, guys? Lattice energy, Mattia, question?
So a more negative energy is stronger.
Correct. A greater lattice energy is reflected in a more negative value, right? Because this is measured exothermically just like electron affinity is. Yes?
Sorry, I just wanted to make sure I heard right. So the greater the lattice energy, the more energy is released from bonding.
Right, and that also results in a stronger bond. Okay, so ionic attractions. Ions form. Ions can form. The strength of ionic attractions is based on charge and distance. Let's talk about covalent bonding. First, the word covalent. Valence meaning referring to the valence shell, co as in to be sharing, occupying the same space. Right? So in any instance of covalent bonding, we are talking about some level of sharing of electrons, and we should specifically state with ionic there is absolutely no sharing. Okay, ionic is complete transfer. Okay, so what's going on in covalent bonding? Well, so here's what's happening. In covalent bonding, you have small, you should say 0 to small delta En. Okay, so let's say you take two atoms and you calculate the electronegativity difference, and let's say you get something like 0.4, 0.5, something. All right. In that situation, neither atom is able to remove an electron from the other. They're both playing tug of war but neither of them has the strength to rip the electron off of the other. So the result is the electrons end up in between. If we look really close at two atoms here, all right, so let's say this is a hydrogen molecule, H2. Right? So in H2, you have two hydrogen atoms. And what's in a hydrogen atom? You have a nuclei, and you have one electron. Here's the other hydrogen atom, and here's its electron. When two atoms approach each other, a couple of things happen. The nuclei attracts the electrons here and here. So both of them do that. So the attraction between the nuclei and the electron is taking place, but you have other things happening. You have repulsions. The nuclei repel each other because both nuclei are positive. So there is a repulsion taking place here, and there's repulsion taking place between the two electrons that are in the bond. So these electrons circulate, being attracted to the nuclei, but also managing to stay out of each other's way because they would repel each other. They are occupying the space between the two atoms, but they have to do so in a way where, they're separated from each other. So because all of these forces are taking place, the electron density, if we plot it, it just kind of looks like a scattered sort of ovalish shape here, right? At any given time when one of the electrons is here, the other electron is not right next to it. It's somewhere else in the space between the nuclei. The concentration of space between the nuclei is between them. Here's where the electrons can be. Will the electron be out here? Yeah, occasionally, but for the vast majority of the time, the electrons will be circulating between the two nuclei. Okay, so you need to understand the three things that are happening with electrons in the bond. Now, if that is taking place, if we were to chart it, say in this chart right here, we plot energy on the y-axis, we're plotting internuclear distance on the x-axis here. So let's evaluate what happens. Nate, do you have a sister? Okay, this is her brother. This is the wrong classroom. Let's evaluate what happens here. If I have two atoms, all right, and let's say these two atoms right here are very far apart. Two atoms that are very far apart, let's say at an infinite distance, they have no interaction with one another. So the energy of interaction will be zero. But as these two atoms start to get close to each other, like see here, they're closer than they were here. As they get close to each other, the attraction lowers their energy state. And as they get closer still, this right here is the minimum energy. This is the lowest energy achieved. But if you start pushing them too close to each other in point D, now you have the repulsions starting to add up. And then here, at this point, the repulsions are greater. They sum up to be greater in magnitude than the attractions. So what determines how long a bond is where the energy is most stable, where it is the lowest. Okay, so bond length is the optimum balance between attractions and repulsions. Basically, on this side, they're too close. On this side, they're too far. The bottom, the most stable energy state, that is what's going to be observed as the bond length and therefore the distance between the atoms in the bond. So, if that makes sense, that's how the bond length is determined. And bond energy is defined as the energy that's needed to to break the bonds. So let's give you a couple other diagrams. What if we see a diagram that looks like this? Compare this new diagram to the previous diagram. Which one of these bonds has a stronger bond formed? The left or the right? The left. We know that the left has a stronger bond because there was a greater release of energy when those two atoms came together. Does that make sense, guys? We did not achieve the same level of stability when the scenario on the right occurred. Yeah, Etienne.
What was the top word say?
It's weaker. And therefore, if it's weaker, this is going to have a lower bond energy. So every bond that forms, these atoms are always in flux. They're actually moving and vibrating. So once they get to that optimum bond length, there's still some oscillations that are taking place. Okay, but the average distance is between these two positions. Okay, so at any given moment, they could be slightly farther and slightly closer than the average. Okay, yeah. Because they're oscillating so much, it's difficult to calculate the exact. So we just have to take that anytime you're given a bond length, it's called the average bond length. Yeah. Okay. Yeah, Nate.
So since the graph on the left is stronger, would the attraction be closer between the two?
It might be.
Okay.
Yeah. It depends on how big the atoms are.
Okay.
Okay. We just all this graph really tells us. Like, if I had numbers on the x-axis, then we would be able to tell the distances. Okay, but I didn't put any numbers on there. Okay. So if you have two atoms where there's electrons being shared, but if the atoms do not have the same electronegativity, it's going to be unequal sharing. Okay, so when there's unequal electron sharing, there is a disparity. And so there's what we call a dipole moment. A dipole moment means like net concentration of electrons, okay? So we draw a dipole moment with an arrow, a sideways arrow, and it points towards the more electronegative element. Now the dipole moment becomes less and less severe as the electronegativity difference gets smaller. So if there's a really large electronegativity difference, then we draw like a larger arrow. So between these, this bond here is the most polar. This is the least polar. If we calculate out the electronegativity difference, the difference between hydrogen and iodine is 0.4. So delta En, 0.4. The difference between hydrogen and bromine is 0.7. The difference between hydrogen and chlorine, 0.9. And then hydrogen and fluorine is 1.9. So when we say that there's a polar bond, a polar covalent bond, it simply means the electrons are being shared, but they are shared unequally. And how drastic that unequal sharing is depends on the magnitude of the difference of electronegativity. Now, I mentioned before, delta En 1.7 is ionic. If the delta En is 0, this is what we consider a non-polar covalent. So think about the elements that are diatomic. These will all be examples of nonpolar covalent bonds within them because they're the same electronegativities. I will say that depending on the textbook, some books allow a range of 0 to 0.5 as nonpolar covalent. So it just kind of depends. There's not a universal consensus on exactly what is a nonpolar covalent bond. The point is, if it's nonpolar covalent, there's a very, very small difference in electronegativity. Very small. So on any kind of test, on the AP exam, you're not going to split hairs between how nonpolar covalent or how polar covalent a bond is. You just have to know categorically what it is. Like, it's pretty clear that if it's N2, H2, F2, these are all nonpolar covalent cleanly because there's literally a difference of 0, right? But you might see another instance where it's 1.8 and you know that's ionic, right? But if it's somewhere in between, the question is not going to be how nonpolar covalent is it. It's more so going to focus on other aspects of the molecule. Does that make sense? Okay. The reason why I bring this up is because the bonding is actually a spectrum. Just like Roy G. Biv. If I said, where's the cutoff between yellow and green? That's very subjective. Well, the cutoff between the types of bonds is subjective, can be subjective, because the traditional cutoff was of 1.7 was decided here, and that's because that's where we see 50% ionic character or greater. And that's kind of where that number came from. Percent ionic character, percent covalent character. Once it achieves 50% ionic character, that's what we consider ionic traditionally. But, like I said, there is some flexibility with that. So, it's situational. All right, so we talked about ionic bonds, which is the result of electron transfer. We talked about nonpolar covalent bonds, where your difference is 0. We talked about polar covalent bonds, where your difference is something other than 0. We now need to be able to portray these, and the first step in portraying these is drawing a Lewis diagram. So, in a Lewis diagram, we're focusing on valence electrons only. And the reason why valence electrons, not total electrons, is because core electrons do not participate in any kind of bonding activities. They're tucked away. They're inaccessible. So they don't really do anything. So, lithium, for example. Lithium has 1 valence electron. You write the symbol, you put a dot. Done. Magnesium has 2 valence electrons. You put 2 dots. Done. All right. Lewis diagrams for individual elements are not that interesting and altogether not that necessary. What is important is when they are bonded. And when they are bonding, we have to obey what we call the octet rule. And this is a generalization that allows us to quickly determine what molecules will look like. The octet rule states the elements are most stable with a noble gas electron configuration, which essentially means 8. 2 S's and 2 P's. It's saying that atoms should have 8 electrons. So, example, NF3. There's 3 fluorines, there's 1 F. Decide on some semblance of symmetry, so I'm just going to put F's here, here, and here. I need to count all my valence electrons. So nitrogen has 5. There's 3 fluorines, or each fluorine coming in at 7, so that's 21 plus 5, so that's 26 total. Place pairs of electrons in a bond, which is shown as a line. Okay, so these 3 blue lines here, those are a pair of electrons each. Step 4, complete the octets of atoms that are attached. So atoms that are attached means the outside atoms. Do the outside atoms first. So this fluorine on the outside, this fluorine, this fluorine. Okay, so I'm going to pause here for a second and see how many I've used. I'm allowed 26 electrons. How many electrons am I showing used thus far? 24. 24 of them are used so far. I have to use 26, and I have to obey the octet rule. So nitrogen, which currently does not have an octet, means it gets a pair of electrons there. Nick.
Is it alright if we draw lines instead of pairs of this?
So the College Board will, I think they'll accept lines as lone pairs. I think they prefer octets. It's one of those things where when you take the AP test and whoever your grader is for that question, yeah, I mean, you're tempting fate a little bit, right? So just put the dots. It's not that hard. Okay. If you have used all the valence electrons that you counted, and if everybody has an octet, then you are done. That is the Lewis diagram for NF3. Okay, so let's draw a couple others. Let's do H2O. So you got 2 hydrogens, you've got an oxygen, so you have 8 total to use. Now, what you should notice or realize that a hydrogen can never be in the center. How come? Why can't hydrogen be a central atom? Yeah, it does have low electronegativity. Hydrogen only has the 1s subshell. If it only has a 1s subshell, its maximum capacity is 2 electrons. So it's always going to be on the outside. So there's water. I have used all 8 electrons that I counted, and oxygen has an octet. Hydrogen does not, and that's okay. CH4. That's going to be 8. So carbon in the center. This is CH4 is methane. 4 bonds, L8 electrons, done. All right, but then you come across something a little different here. We have a polyatomic ion, right? SO3 with a -2 charge. If it's got a -2 charge, you have to take that into account when you are counting up the valence electrons. So we count 6 from sulfur. There's 6 apiece with each of the oxygens. And if it is negatively charged, that means it has gained 2 electrons. So you have to count those in the total. So you've got 18 plus 6, 24 plus 2. So we have 26 now. Sulfur in the center. 3 oxygens. 3 bonds. Outside octets first. All right, that's 24. And then the last pair goes on the central atom. Now, when it is an ion, it needs to be signified with brackets with the charge in the corner. Is this all coming back? All right, Lewis diagrams, right? A lot easier second time around, right? Okay. Then you have weird stuff. Sometimes you have an oxoacid. So an oxoacid is when you have a nonmetal with oxygens and hydrogens, right? But the number of oxygens is greater than the number of hydrogens. So look at this formula here, HClO4. It's got hydrogen, it's got a nonmetal, it's got oxygens, but there's more oxygens than hydrogens. This is what we call an oxoacid. And the point of oxoacids is that the hydrogen is attached to the oxygen, not on the center. So let's add this up. 1 from hydrogen, 7 from chlorine, 6 oxygens, so you've got a total of 32. Chlorine in the center, 4 oxygens, 4 bonds. The hydrogen has to go somewhere. I'm going to put it here. That's called perchloric acid, and it's very, very nasty stuff. I can't even buy it anymore. I mean, I can, but it's like the shipping cost on it is ridiculous. It's not worth buying it. But it's a strong acid. Okay. Other oxo acids. Nitric acid. Sulfuric acid. Phosphoric acid. Look at these. They all follow that same pattern. Do you guys see that? H's, O's, but more O's than H's. Okay. Nope. What would chemistry be if there weren't exceptions? So, I would argue it's not fun, because if there's no exceptions, then there's nothing to really think about. Okay. So, of course, there's exceptions to the octet rule, right? So, the exceptions are hydrogen, beryllium, boron. Hydrogen has one pair on it. Beryllium will have two pairs. Boron can only have three pairs. Oh, they're actually right here. It's already here. So there are exceptions. Some atoms are too small. Too small. If they're too small, that means electron pairs will be too close to each other. That means repulsions will be too high. Okay, so for stability reasons, we only observe this number of pairs for these elements here. But sometimes we have what's called an expanded octet. An expanded octet occurs if the central atom is in period 3 or higher. Period 3. So look at period 3. I want to see sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. Okay? What is notable about period 3 is they have access to a D subshell. Remember electron configurations. The D subshell first appears in the third period. There is no 2D, there is no 1D. So because the D subshell becomes available in period 3 and after, anytime the central element is a third period element, that is capable of expanding. So let's try these examples here. PCl5. You got 5 from phosphorus. You got 7 from chlorine. So 5 times 7, 35 plus 5. So this is 40 valence electrons that we're going to use. So symmetrically, phosphorus, chlorine, 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 chlorine. 5 bonds. And then since I have 40 electrons, 40 is divisible by 5. So basically I have 5 groups of 8. Everybody has an octet. Everybody's happy. Phosphorus was capable of expanding because phosphorus is a third period element or greater. Okay. SF6. No, 4. SF4. So 6 plus 4 times 7. So 28 plus 6 is 34. All right, so sulfur in the center. Fluorine, 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 fluorine. Bonds. 4 bonds. Outer octets. Okay, at this point, I have used 4 groups of 8. That is 32 electrons. I have to use all 34 that I counted. So the last pair, stick them on the central atom. Right there. Now, the most you're going to see is 12. All right? And this has to do with the geometry configurations of the atoms. Think of an XYZ plane, an atom, front, back, left, right, left, and front, back. Wait, that's it? Up, down, left, right, front, back. Right? There's 6 possible places around an atom in 3D space. Okay? So that's 6 pairs of 6 bonds, 12 electrons. How are we doing? Okay, so far, Lewis diagrams? Okay, I want to get to a certain point so that we can be prepared for our next lab. So that's how we're kind of rolling through here. Sometimes the Lewis diagram doesn't agree with the rules that we just laid down. So let's look at NO3. 5 plus 3 times 6 plus... What do I do with that minus 1? Add 1. Okay, so 18 plus 5 plus 1 is 24. So nitrogen, 3 oxygens, 3 bonds. If I fill up my outer electrons, I have used up 24, but there's a problem. What's the problem? No octet on nitrogen. Well, that can't be. So if that happens, if you have run out of electrons and you have not fulfilled the central atom's octet, that means a pair of electrons is not necessarily a lone pair. You're just going to rewrite them as a double bond. Okay? And here's the thing. I decided to put that double bond on the right-hand side, but I could have very easily put that double bond on the left or on the top, because the 3 atoms, the oxygens, are identical. When the outside atoms are identical and you don't know which one it is that it goes on, that means that double bond is actually not just on that oxygen, it's actually averaged between all of the oxygens. So that means this shape is not technically fully correct. The Lewis diagram is actually an average of these 3 possibilities. And that's what we call resonance. It's not a true double bond. The double bond is averaged between the 3 positions. If the double bond is averaged between 3 positions, that means all of those bonds are identical. They are all 4/3 of a bond. They all have the same strength and the same length. Now, you might see resonance drawn this way. See what's happening here? See how you have like a fractional bond on each of those positions, right? You might see it that way. So if you see it, that basically means the same thing as this. Okay? So it's just like a shorter way, a quicker way of showing resonance. Yeah, too.
Are we allowed to show it that second way?
Sure. Sure. I will say there's some pitfalls with doing it that way, though. And the pitfall is when we start drawing it this way, do you see how I still left one of these oxygens here with not a full octet? Okay? You have to get your electron count right. So if you do draw it this way, you just got to make sure you don't put to the last 2 dots here, because that means you're actually increasing. That means you're not accounting for where the double bond is. Does that make sense? It's simplistic to do this way. It's kind of more foolproof to do it this way. This is more like, it's kind of like the other instance that came up. Will the grader, is he grading your test before he had his coffee or after? All right, so it's a little risky. I don't know. Maybe I'm interested in that statement. I think it's safer to do it this way. Okay. And the brackets with the charge. And the brackets. A lot of writing. Yep. Okay. Yes.
Can you just put the brackets of the entire thing, like you have to do it over each individual one?
It needs to be done over each individual one because there's 3 separate structures that you're drawing. Okay. How far can we? Okay, so I think we need to go through this and then we'll be done, because this is important for you to be able to correctly draw loose structures. Okay, but before we do this, I just want to have you guys draw a couple first. So take a second and draw these. All right, so did you guys come up with this? For sulfate? Okay. And then for SF6, this one actually works out to be all 8s on the fluorines. This is where it's tempting to draw the lines for your lone pairs. when you get to that point. Did you get that? Okay. I want to give you guys some weird situations first before we go over formal charge. How would we draw this guy? H2CO. Well, we have 2 plus 4 plus 6. Okay, so we have 12 total. When you don't know what element is going to be, because there's 3 elements, right? How do you know which one's going to be in the center? The answer is the one with the lower electronegativity. So it can't be hydrogen. So between carbon and oxygen, which one has a lower electronegativity? Carbon. So it's going to be carbon in the center. Now, is this an oxoacid? Because I seem to remember oxoacids having H's and O's also. This is not. How come? Right, the ratio is not correct. Oxoacids have more O's than H's. Here, there's more H's than O's. So this is not an oxoacid, which means the H does not have to be on the O. The H connects directly to center. Now, if I count my electrons, 2, 4, 6, 8, 10, 12, I've used all 12, but this is not allowed because I'm violating the octet rule for carbon. So what do? I'm going to need a double bond. So erase one of those pairs of electrons off O and rewrite it as a bond in between. Okay. So, you know what? Actually, this is a good stopping point.